12 million people. That's how many are affected by medical diagnosis errors each year. From these, approximately 80,000 die from complications from these misdiagnoses. In some cases, it's not the doctor's fault. Some tumors are indistinguishable from perfectly normal conditions, and there's nothing that the doctor or anyone else can do about it. Well, any human can do. Bring artificial intelligence and machine learning into the picture. Look at the pictures below. Can you tell which ones are melanoma and non-melanoma? Probably not. Some of them just look like dirty molds. By simply using pre-existing medical data, machine learning algorithms are able to diagnose tumors more accurately than even professionals can in the field in a much more fast and efficient way. With the advent of new machine learning algorithms, this diagnosis is only getting more and more accurate annually, and it simply depends on who uses the algorithm correctly in the field that they're interested in. By using generative models like variational autoencoders, along with semi-supervised learning, important patterns can be recognized that can distinguish tumors from non-tumors. Let's start off with variational autoencoders. There's usually one major roadblock that prevents medical professionals from taking machine learning algorithms into more consideration: the lack of accessible data. Machine learning algorithms need a lot of data to train on in order to be extremely accurate. Precision is key in these specific instances because a misstep can lead to the misclassification of tumors, which simply leads us back to square one. This is why generative models are extremely important. They synthesize these images that are so important for the model to train on. Essentially, the generative models aim to use the limited existing data to create new images to expand the dataset even further. One of the most common generative models are variational autoencoders, and they're often used for classification in the medical workspace. Before we go into variational autoencoders, I want to give a quick summary on what autoencoders are. So first, remember that data is really complex. There is so much information packed into one picture that it can be difficult to train on with all the features without overloading your computer. It's important to recognize all the points on the picture since they can provide key instructions on classifying whether something is a tumor or not. Through dimensionality reduction, which aims to reduce the number of features that decode the data, autoencoders try to circumvent this problem. Through dimensionality reduction, we will be able to do this. This is the picture that is shown. As shown here, there are three distinct sections of autoencoders: the initial data, the encoded data, and the decoded encoded data. The goal of the encoded data is to keep the maximum amount of information when encoding. When removing the features, information will get lost, so it's vital that the most pertinent features are the only ones that are kept. On the other hand, the decoded encoded data aims to use the encoded data to reconstruct the original images with all the features. The accuracy of the decoder is measured by the reconstruction loss, which checks how close the original image is to the reconstructed image. The number of features encoded can be tweaked using a hyperparameter, depending on whether you want to optimize for storage or accuracy. Remember that the more features that there are, the more storage is necessary, and for the less features that there are, there's less accurate and more inaccurate the final image will actually be. So variational autoencoders actually take this one step further. Instead of using the decoder and taking in the entire encoded data vector, it simply takes in a sample of the encoded data, sampled from points on a normal distribution. I won't really get into the specifics because it requires a bit of statistics and linear algebra, but essentially, the decoder now aims to generate these images by minimizing the regularization loss based on how close it actually emulates a normal distribution. So, with this additional regularization loss, these sampled points can provide meaningful content for further training. So this loss below just simply adds from the reconstruction loss that we talked about before in the autoencoders, and it's often called the Kullback-Leibniz divergence, or how far it actually differentiates from the normal distribution. So this variational autoencoder is then checked on continuity and also completeness. So continuity is how close these related points are actually together on the encoded space, and completeness is how close these sampled sampled data will actually provide meaningful content. So the data that's generated by these variational autoencoders is unlabeled, meaning that it does not have a label associated with these images. So with this unlabeled additional data, we can add it in with the labeled data from the beginning in order to create a semi-supervised image classifier. So essentially, a semi-supervised image classifier works by training both the unlabeled and the labeled data so that the model can use both the variational autoencoders and also the data that's provided by the medical data sets in the first place. But remember that the variational autoencoders, there's so much data that is inside of there that it basically trumps how much data there is inside of these medical data sets. So the application of this technology is extensive, as there are many tumor diseases that are out there that are extremely hard to recognize. Right now, I'm working on a project for diagnosing melanoma tumors using variational autoencoders and semi-supervised classifiers, and I'm only just starting to realize the implications of this. So, now that you have newfound knowledge on the topic, look back to the beginning of this presentation. Those 12 million people can live healthier and stronger lives with just a simple generative machine learning model and image classifier. Thank you.